Hello everyone, it's May the 9th. Alright, I thought about this problem a little bit last night, but the answer is I don't know. I have no clue. Yeah, I have no idea. So I think I'm gonna go through the hints today if we get there. Let's first solve this. We have a spiral matrix again. This is to create a spiral matrix. We have a positive n, generated n by n, filled by elements. So it'll be exactly the same thing, but actually it's not exactly the same thing. I think for this, we can actually use the automatic rotation. Yeah, I think automatic rotation will be very, very handy in this one. Let's try automatic rotation. All right, so res equals to from 1 to n, so I can do 0, right, times n, and for this in range n, okay? And then we say for this in range n times n, okay, I, j, di, dj equal to 0, 0, 0, 1. And oh, there should be I in range, not I, v in range 1 to this plus 1, okay? And I'll say res ij equals v, and then if I plus di is smaller than 0, or I plus di is larger or equal to n, or j plus dj smaller than 0, or j plus dj larger or equal to n, or res I plus di, j plus dj is not equal to 0, then we need to change direction, which means di dj equals to dj minus di, right? Yeah. And then I plus equal to di, j plus equal to dj, and then we'll return res. Okay, let's give this a shot, see if it's working. Yep, I think this is working. Actually, I can do all the tests. The automatic rotation strategy from yesterday works extremely well with this problem. All right, let's copy this, do this, submit. I think probably use the same automatic rotation, right? Yeah. Ah, if not, or oh. Okay, so we're done with this. Now let's get back to this one. All right, so I don't have an idea. So let's see, similar question. Max exclusive for hash table, bit manipulation, prefix sum. What do you think? It is bit manipulation, hash table. Yeah, because what I realize is it's basically in exclusive OR, right? So the question can be simplified to this. We want to find we want to find, right? I want to find so we want to find all subarrays, right? We want to find all subarrays whose exclusive or whose exclusive or equal to 0. That's it. That's what we're looking for, right? So given 4, 3, 1, 2, 4, want to find the exclusive or that's equal to 0. Like ending at this, how many exclusive or? Ending at this, how many exclusive or? That's what I understand. And ending at this is not going to do. And this, we can exclude all of these. And this, and basically we just want to find, because this one is 1, right? And exclusive or 1, exclusive or 1 is 0. So we want to find ending at 3. How many substrings exclusive or ending in 1, right? And for 2 is, for this, how many substrings ending in 1 exclusive or value is 2. Yeah, like 3 and 1 exclusive or is going to be 2. But how can we do it fast? Because now we're looking at O(n) squared, and that's definitely not what we want, right? I don't know. I mean, I'm still kind of thinking this way. This is what I got stuck yesterday if I do exclusive or. And the thing is, the ones I have previously, how would it help? Like if I know, yeah, like if you want to find, but technically you only need, no. Yeah, I'm still stuck in the same position. Let's see. Yes. Oh, compute the prefix exclusive for every index. Then the exclusive subarray is equal to 0. Then the exclusive of subarray left and right is equal to 0 if prefix left exclusive of prefix right is equal to 0. That is a key insight. Wait, is that true? So A exclusive of B exclusive of C. Okay, now I have B exclusive of C. So let's test D. Actually no. I want to know what is this? What is B exclusive of C? So I know A exclusive of B. I know A exclusive. I know A. So to know B exclusive of C, what do I do? I say I do A exclusive of B, right? Exclusive or A exclusive of B exclusive of C. Does this work? What's the rule for exclusive or? Exclusive or associative? What's the rule? It's both commutative and associative. Okay, it's both commutative and associative, which means this I can simplify to what is associative. What's commutative? Commutative is rotate, right? Commutative, yes. Associative, yes. Okay, so I can say A exclusive of B, exclusive of A, exclusive of B, exclusive of C. And I can rotate. So A exclusive of A, B exclusive of... Isn't that when you just get C? This isn't right. That's not right. No. I want to know B exclusive of C, right? So I have A exclusive of B exclusive of C. If I'm exclusive of A, then I have B exclusive of C, right? So that means to get this, I use, right, to get I to J, right? To get I to J, I need to do I minus 1, right? Exclusive of J. So it's the same. It's the same as yeah, it's the same as sum. Okay, so that is a very important. Okay, I think let's see if we can get it from here. We use exclusive or, right? So if we use exclusive or, and it serves the same way as prefix sum, right? Basically prefix sum. So for things ending at a value, I want to know how many of the previous subarrays whose exclusive or value is 2. And how do we do that? I mean, I already know how to get exclusive or of this, of everything, right? I know everything. Maybe we can, count, right? Let's say the value is 2. How many exclusive or? It's like a hash map. It says hash map, right? So the hash map, I have exclusive for something and something. Okay, so I say I have a whole list of exclusive or value. But now I add one, right? I add one. How does that change? Well, you will have a new exclusive or value, right? And then what? I know all the previous exclusive for. I know 1. I know 3 exclusive or 1. I know 4 exclusive or 3 exclusive or 1. I know this, right? I can compute all of this. And all I want to know is which one is equal to 2. Right? I mean, think about it, it's just a prefix sum, right? We just want to find the subarray sum that's equal to you. Don't think about exclusive for. Think about sum. The prefix sum is equal to you, and we just want to know how many. And let's say we know how many. And then when you add yours to the whole thing, how does that change? We'll have a new prefix sum ending in U. Okay, that's fine. We have a new prefix sum. Oh, 2 sum, right? 2 sum. Let's say you have all the prefix sum, all the prefix, right? I have the prefix exclusive or. Okay, I think it's 4. 3 exclusive or 4. What's 3 exclusive of 4? Is that 7? 3 exclusive or 4. 4 is 1 0 0. 3 is 1 1. Yeah. And exclusive of 1 is 1 1 0. What's 1 1 0? 1, 0 is 6, right? And then, okay, that's what we have. Okay, that's what we have. Now I have 2 coming out. I want to know what exclusive for previously will get us 2. So some value, exclusive of some value equals 2. Which is the same to say this value exclusive of this value, we need to equal to somebody in it. Wait, hold on, what does that mean? Well, it has to, so, oh yeah, so it has to be this, right? It has to be this. So I do 6 exclusive of 2 equal to 4. Then we search previously if 4 is in there. And then we count how many 4s is in there. Ah, I get it. Yeah, because it's a substring, right? Which means I need something, right? I need this. I need something, prefix, pre-exclusive or, I to exclusive or. Hold on. Let me do this one more time. We want, right, a range exclusive or to be 2, and a range of exclusive or which has to end at this is the prefix this exclusive or 6 must equal to 2. That I can move 6 to the other side, which means we want prefix exclusive or I equals to 6 exclusive or equals to 4. Then if we have a counter of how many 4s there are, then we can know how many of the indices previously we can take. So that's how we do it. Oh, this is... Woo-wee. The hint is quite useful. All right, so we need a pre-exclusive or. Okay, I will do num0. That will be the first one, and we need a counter. Right, and we say counter is gonna be counter. And counter num0 equals 1. That's the first, right? And res equals 0. Then for I in range 1 to len nums. Okay. Then what we're gonna do is res plus equal to counter something, nums I exclusive or pre-exclusive or I minus 1. All right, once we're done, pre-exclusive or dot append pre-exclusive or minus 1 exclusive or nums I, and now return res. Okay, let's take a look at this. Actually, I can just do num0 here. I don't need this. The first one's not right. Oh, I didn't update counter. Counter. Right, counter prefix this plus equal 1. That is interesting. There are still some kinks we need to work out. Oh, it's and. No, it should be exclusive or. Damn it. I think it's the last one. If you add the last one, we're missing the last one. Right? Because when we hit the last one, I tried things ending like this. Okay? Which is 2. Right? But it should count, right? Because I need 4 and 4 is 0, so prefix I should start with 0. There we go. This is right. Yep. But why my result is still wrong? Oh, because you are starting from I, and when you do this, I don't think it should be I minus, it should be prefix minus 1. There we go. That's right. So we update this, and then we append, and then we do the counter. Okay, so the hint is very helpful. Key intuition is that, well, there are two key intuitions. There are 2 key intuitions. First, the problem is equivalent to finding all prefix, all subarrays whose exclusive OR equals 0. Now, I get this one from last night's effort. 2, a prefix exclusive OR behaves exactly the same as prefix sum, in which the exclusive OR from nums I to nums j is equal to prefix j exclusive OR prefix I minus 1. Now this insight I missed. With this insight, the problem is immediately simplified. right? I mean, it's simplified because to find all the subarray ending at I, whose exclusive OR is 0, we just need to find all subarrays ending at I minus 1, whose exclusive OR is equal to nums I. That means we want prefix j, right, exclusive OR prefix I minus 1 to equal to we want to find all the j's such that equal to nums I. This is equivalent to finding all prefix j whose value is prefix I minus 1, exclusive OR nums I. We can use a counter to keep track the number of each prefix j, and the problem is solved. And we'll run it all in time. Oof. This is good. This is a hint. All right, don't be so cocky because we haven't tried on other things yet, but I think this is right. Let's just give it a shot. Yep, that is the solution. Very good. Prefix exclusive OR. Yeah. Yeah. Counter. Oh, yeah, you don't even need to keep. I just need to keep the last value. That is true. Yeah, that's exactly the same. There are better solutions, not better implementation. Let's implement that. Ooh. Same as solution 1, but with better implementation. We don't need to keep the entire prefix exclusive OR array. Only the last one will suffice. Reference Leet 215. Okay, so we don't need this, we just need this. Ah, yeah, now we can do this. P exclusive, well, let's do that, all right? And rest equal to this and, oh, I don't even need I. For ending nums, rest plus equal to counter n exclusive all, P exclusive all, all right? And P exclusive all equal to n and counter P exclusive all plus equal 1 over time. Oh my god. This is so much simpler. It is a medium problem, right? The inside is harder to get, but it is, it is the same problem as the prefix. Yep. See, faster, so we don't have to set up the whole array. Okay, we move on to the next one. Good question, very good question. Minimum time to complete all tasks. Maybe I'll just read the question and then call it a day. I'll stop brooding on this. There's a computer that can run an unlimited number of tasks at the same time. You are given 2D integer array where start and duration indicates that the ith task should run for a total of duration seconds, not necessarily continuous, within the inclusive time range. Interesting. You may turn on the computer only when it needs to run a task. You can also turn it off if it is idle. There's the minimum time during which the computer should be turned on to complete all tasks. The minimum time duration. So what we're saying is we have a start and end, and each task must run in this time range, but not necessarily all the time. Just within a time range, we can run the task at any time. Okay, and all the tasks can be run at the same time. So the first one we have 2, 3. So we have a task need to run between 2 and 3. And another one between 4 and 5. And another one 1 and 5. So we can turn the computer on from 2 to 3. We can finish task 1, and then we can do one portion of task 3. And then we do task 2, and we do another portion. Wait, inclusive time range. Wait, hold a second. The first task can be run in the inclusive time range 2 to 2. We start at 2, we end at 2. Wait, what the hell is that? The second can be run in 5 to 5. The third can be run in a 2 inclusive time range. Wait. For a total of duration seconds within the inclusive. Wait, so 2 to 3 is 2 seconds? The second, the third second. I think that's what it means, right? The second, the third second. So 2 to 3 counts as 2 seconds. So 1 to 5 will count as 5 seconds. Okay, then second example. 1 to 3, 2 to 5. I mean, to try to do this, I guess you have to do something similar to, I don't know, a range, right? So I have 1 to 3. It might be easier to do this. Okay, 1, 2, 3, 4, 5, 6. So we have 1 to 3, so that's a 2 second range. 2 to 5. And 5 to 6. Okay. So 5 to 6. Remember, 5 to 6 is 2 seconds. Damn, that's okay. So 5 to 6 is 2 seconds, so it has to run this. So this one has to run between 5 to 6. And then 1 to 3, I can run a 2 second task. 2 to 5, I need to run a 3 second task. And they have overlap, so we need to utilize this overlap. So I have 2 seconds overlap. So the first task can finish in this, and the second task can finish by 4. So I do 2 to 4 and then 5 to 6. So this requires 3 seconds. This requires 2 seconds. So my answer is 5 seconds, but the answer is, Oh, I do 2 to 3. I do 2 to 3, so that's 2 seconds. We finish the first, and we finish the 2 seconds of the second. And the last second, we do 5 to 6. So that's 2, so we get us to 4. Huh. Yeah. Okay, so we do the range first, right? We do the range first. Let's do the first one again. Let's see. 1, 2, 3, 4, 5. So we have 2 to 3, 4 to 5. We have 1 to 5. So these are the ranges, okay? And we want to find overlap. Because overlap means we can parallelize, right? So how do we find overlap? Which means what we want to find is at a certain point, how many tasks can be stacked at this point. And in here, I have one task. If I do indices, right? So at this point, I have 2, right? Index is 2. And at this point, my index becomes 0 and 2, right? And at this point, there should be still 2, right? And this point is 1 and 2. And the last point is going to be empty. All right, this is like line sweep. That's kind of the results we have. So we now know that we have overlap in this portion and in this portion. All right, so in this portion, we have 0 and 2, so they both can execute. Then we want to know how long can we execute this. All right, then we execute as long as we can, as long as necessary. So we can see at this point, are you saying we should get the maximum overlap out first, right? 0 and 2, and a task 0 is not being done, task 2 is not being done, and task 0 and task 2, the minimum. We execute the minimum amount, right? The minimum amount, because the remaining might have other overlap to work with. Okay, so we execute the minimum, and task 0 is done. So we left with task 2, which has 1 remaining. And the computer runs at 1. And now we find the second overlap, 1 to 2. Now 1 has 1, target is 1. So when we do that, we also say we're going to run. Well, when this is done, actually we shall, because that'll be a new time point, right? If we have just a large one. When we finish, then we shall have a new time point here. Yeah. But I already have it. That's fine. And then, but how about this? So we don't have a time point here. But anyway, so we do this, and then we do 1. And it will finish task 1. So this will have task 2 as well. Now everybody is task 2. Right? Everybody is task 2. Then we just pop anyone out. Oh no, task 2 is done as well. Because task 2 only has 1. So now task 2 is done. So this is done. Then no task is remaining. So we have answer is 2. So what do you think? I think is a line sweep. I think for this case, we have we have tasks, right? 0 requires 2, 1 requires 3, and 2 requires 2. And then we have, at this point is 1, 2, 3. That's a 0 is here. This is going to be 0 and 1. This is going to be 1. This is going to be 2. Okay, so that's our starting point. So if we do a priority queue, we'll have 0, 1, 0, 1 starting at 2. Oof. 0, 1, 2 at the beginning. All right, and then we have, I don't know, 0 is 1, 1 at 3, and 2 at 5. Right? So this one pop out. Okay. So 0, 1, 2. Now we see 0 and 1. Smallest is 2. Right? So I will execute. Well, we're at position 2. Right? We're at position 2. So we also need to see if it's possible, right? The largest that we can execute, because it might be, yeah, we need to execute the maximum, right? So we have 0 and 1. We're at position 2, right? We're at position 2. The maximum for 0 to execute from position 2. So 0 has a 1. So the maximum 0 is 1. And if we execute, but position 2. So 0 has to execute up into 3. So 0 we can execute from 2 to 3. So 0 we can do 2 seconds. Right? And then 1, no wait, 0 is here. Yeah, 0 we can execute 2 seconds. For 1, we can execute, because I'm at 2, so we can execute 1. 0 we can execute 2 seconds. For 1, we can execute. Oh, hold on. It depends on the smallest of them. Like all the overlapping things, what is the smallest right? So the smallest right is 3, which means at this position, the maximum we can execute is 2 seconds, right? And then we take a look at the time, right? What is the smallest here? We'll execute the smallest, right? Smallest is 2. So we execute the smallest, which means then 0 is done, 1 become 1 left, and we progress the time here from position 2. So we'll basically this is out. Now I put it in, so it'll be 1, it'll be 3, right? That's the new position. 1 and 3. Okay. The current starting position, right? One can start here, one can start here. Next. Doesn't matter. If 0 comes out, I say, yeah, 0 is done, so we don't have to consider 0 anymore. So next, we say 1 pop out. 1 is at 1. 1 is at 3, right? That's the case. This has to be 1 and 2, right? This has to be 1 and 2. So the ending position is a little bit tricky. Right, the end position is a little bit tricky. Because it's inclusive. So I think this is not just 1. This is 0 and 1. So these two both are 0 and 1. Okay, both are 0 and 1. But when we do priority queue, we have to choose the smaller of this, smaller of the starting position, so you get more time to execute. I think this might work, but we'll see. I'll leave this for tomorrow. All right, that'll be it. I'll see you guys tomorrow.